Cool. So hello, everyone. Welcome to the fourth edition of the Academic Fringe Festival, TAF. My name is Jie Yang, Assistant Professor in the Web Information Systems Group here at TU Delft. I'm a co-director of the Delft Design at Scale AI Lab, and I lead the Human Language Technologies Initiative at TU Delft, which is very much related to the theme of this speaker series, where we focus on the knowledge and language aspects of human-centered AI. So human-centered AI, as you might have heard about it in many different occasions, I believe, is a very broad topic with an ambitious goal to design and develop AI systems that can support human activities in a reliable, safe, and trustworthy manner. It requires research and innovation from a broad range of disciplines, including but not limited to computer science, human factors, ethics, philosophy, psychology, sociology, and specific application disciplines. In the past, we have organized 3 editions of TAF, and you can find the videos online on our website if you're interested. Now, in this series, we will focus on the knowledge and the language aspects, which are key concerns in making AI systems understandable to humans and allowing humans to interact with AI. Now, on these topics, we have invited a list of speakers whose work has made foundational contributions to knowledge and language. The series will go from today until April 17th, with an invited speaker introducing their recent work every week. So this week, I'm thrilled to introduce our speaker, Diego Calvanese, full professor at the Research Center for Knowledge and Data, Free University of Bolzano, where he leads the Intelligent Interaction and Access to Data Research Group. He's also a Wallenberg guest professor in artificial intelligence for knowledge management at Umeå University in Sweden. Professor Diego's research interests concern foundational and applied aspects of artificial intelligence and databases, notably virtual knowledge graphs for data management and integration, ontologies, knowledge representation and reasoning, semantic technologies, and data-aware processes. Diego is the author of more than 400 referred publications with over 35,000 citations and H-index of 74, according to Google Scholar. He's a fellow of European Association for Artificial Intelligence, a fellow of ACM. He's the originator and co-founder of OnTopic, the first spin-off of the university, Free University of Bolzano, founded in 2019, and developing solutions and technologies for data management and integration based on virtual knowledge graph, which today Professor Diego will introduce to us. Which I have been looking forward to since we invited him from the beginning. So again, all participants, feel free to ask questions during the presentation, but please do so in the chat. And then after the presentation, you can unmute yourself for questions. Now, without further ado, let's welcome Professor Diego Calvanese. Thanks a lot, Diego, for being here, and the floor is yours.
Thanks a lot, Yves, for inviting me to give this presentation about a topic on which I and also colleagues have been working since many years. Actually, this topic somehow dates back to my PhD, which was in '96. I finished in '96, where it was quite theoretical, the work. I mean, still, it was the name was different. We didn't used to call them knowledge graphs. We called them at that time ontologies and description logics, but it became more practical, still with theoretical foundations, which we started in 2005 with a AAAI paper, which was actually quite well received. We received also an award for that paper 15 years later. This laid the theoretical foundations for what we now call virtual knowledge graphs. And at that time, we called it ontology-based data access. So querying data through ontologies, which is the topic we are talking about here. Let me share the screen and then. Okay. Now can you see my screen?
Yes, I can see it. Not in the full screen.
Yeah,
mode.
no, now let me move to the full screen, which is a bit slow. I don't know why my machine has some. Okay, now you should see my full screen, right?
Yes, very well.
Okay, great. So yes, so this topic, as was saying, dates back to quite some time, and it became quite more applied around 10 years ago when we started to build systems here in Bolzano for data access using ontologies. And this is at the base of what we now call virtual knowledge graphs. And initially the work implemented essentially techniques that we were designing theoretically, the algorithms for query answering. But it turned out quite soon that, first of all, we needed optimizations, and this was one aspect. And then when it became more practical, we started to apply this technology in different settings. It became clear that setting up such systems is not an easy task. So the design of the ontology and what we'll see is the mapping component of such systems turns out to be quite challenging. And that led then us and also other groups to develop tools and let's say also methodologies and an approach to make the setup and the development of such systems easier. And that's what I want a bit to talk about today. So now this problem of knowledge graphs and virtual knowledge graphs is related to the problem of accessing data, because we all know that data management is a complex challenge in complex organizations. It might be large companies or public administrations, which often have different data sets that have been created independently and developed for different purposes. But then at some point, this data, which is typically heterogeneous and needs then, and developed a set for different purposes by different people, needs to be put together and accessed in a coherent way. And this is required for many tasks nowadays, especially for data processing pipelines, which aim at analyzing, monitoring, and doing prediction of this data. And in order to do so in an effective way in these large organizations, one needs to integrate the data coming from different sources and have a uniform access to this. And this is a problem that is challenging. And this is what we call the data access problem. And that's the problem we are looking at here. Now, how can we address this complexity that we have in data access? Just to get immediately to the point, the approach that we have been pursuing and the methodology that we propose is based on 3 key ideas. So the first one is that we don't want to expose to users the actual data sources because they are complex and they are not meant to be used in an integrated way. So what we do is instead we expose to users and to applications what is called a knowledge graph. So a knowledge graph is a coherent, uniform view of the information, which is expressed in a vocabulary, so in terms that the users are familiar with, and that have the basis in what is called a domain ontology or a global schema. So the user sees this knowledge graph expressed in a vocabulary that the user is familiar with. So if, for example, we have geologists who talk about drilling, I mean, I just mentioned this because it was a concrete use case in some projects in which we're involved. They know about drillings, they know about oil wells. So that's the terms they want to use. And so when we need to provide them the information they want, which is stored in many different databases, they can use these terms in their queries and in the way they access this information. The second important point is that the data is still stored in these data sources. So we need to establish a connection between the ontology or this global schema and the actual data sources. This is done through mapping. So we map these data sources to the global schema, to the ontology, so as to provide to the user the actual data they want to access. And the third important idea is that we want to keep the data in the sources. We don't want to materialize the data in a new view in a knowledge graph. So the knowledge graph is not really materialized. Why? Because this has issues of efficiency, and often in settings where the data sources are very large and possibly also very dynamic, so data changes often and fast, materializing the data is quite costly, and you would not be able to have fresh data in the materialized view. And therefore, the approach that we follow is not one of materializing the data, but of essentially translating the requests down to the data sources. So we keep this data virtual at the level of the knowledge graph, and we provide access by translating the requests, the queries that the user poses over the ontology, down to the data sources and provide the answer then to the user. And this is essentially the idea of this virtual knowledge graph approach to data access, which has also been known as ontology-based data access, or OBDA. And when the emphasis is on the integration aspect, then it's also being called ontology-based data integration. So the ideas that I outlined before give rise to this conceptual architecture, which we call the virtual knowledge graph architecture, where, as you can see, we have this knowledge graph, or virtual knowledge graph, VKG, as we abbreviate it, that presents the data in the vocabulary of an ontology. This knowledge graph is mapped to the data sources, to the heterogeneous data sources. By heterogeneous data sources, in general, we mean relational data, but also CSV, JSON files, possibly XML files, possibly data on the web. The point is that, in fact, we wrap this data and present a relational view of the data. And that's what to which we establish the mapping. So we have a relational view of this data that is essentially depicted here in this slide by this database symbol that you see on the right. And we map this relational view of the heterogeneous data sources to the ontology and to the knowledge graph. And then users, which might be either actual users, but also different kind of applications and business intelligence tools that want to access this integrated data. They query the data in some language. We will see the language that we propose is the SparkQL query language, which is a standard language in the context of the semantic web and in semantic technologies. And the system delivers the result to the user, which can then process these results for the various purposes they have, for example, business analytics. So that's the idea of the virtual knowledge graph architecture. Now, let me briefly motivate a few of the components of this virtual knowledge graph architecture and why we rely on such architecture. So the first consideration is about the ontology. So an ontology can be seen as a structured and formal representation of the relevant concepts in an application domain and of the relationships that exist between these concepts. And in this virtual knowledge graph setting, the ontology has essentially two purposes. One, I already mentioned, it defines a vocabulary of terms that the user is familiar with, and these terms denote classes and properties that the user wants to see in their domain. And the second important aspect of the ontology is that it is actually, it encodes domain knowledge. So it encodes background knowledge about the domain of interest, and this knowledge is essentially machine processable, and it can be used to enrich answers to the requests that are posed over the ontology itself. So not only you have a vocabulary that is with which the users are familiar, but also you have knowledge embedded in this, and this knowledge can be exploited. And in addition, there are many ontologies that are available, standard ontologies, but in addition, one can also build custom ontologies for specific domains, and they can be combined with standard ontologies that are available for many domains, for example, the biological domain, the medical domain, but also in the oil and gas domain, the example that was mentioned, in e-commerce domain, there are many ontologies that are already available and can be used for this purpose. The second aspect is the knowledge graph, so that this global schema is presented in terms of a graph, a knowledge graph. This is different from the traditional approaches to data management and data integration, which actually rely on the relational model, which is the standard model used also for data integration. Instead, using a knowledge graph gives more flexibility, because one does not need to commit early to a specific structure, which one would have to do if you have tables that you see at the level of the global schema, at the level of the ontology. And therefore, a graph view of the data is better able to deal with heterogeneity and also with missing and incomplete information, and also with the dynamicity of such a setting, for example, an integration setting, where new sources might be added to the whole architecture and have to be incorporated and in the integration system. And a graph approach is better suited to deal with such dynamicity and heterogeneity. The next aspect are the mappings. Again, if one looks at traditional approaches to data access integration, they often rely on so-called mediators, which are specified, custom-built code that is designed and developed in order to access specific data sources. Instead, using mappings provides a declarative specification of the relationship between the sources and the domain ontology, and not a code. And this has the advantage that one can better understand, it's easier to understand the relationship between the ontology and the data. One can easily follow a so-called incremental approach to integration, because when a new source is added, one just adds mappings to this new data source. And also the mappings are machine processable, and different from arbitrary code, procedural code, they can be analyzed and they can be exploited also for optimizing the access to the data source and for query optimization. That's what we actually do in our systems. The next point is virtualization. Again, in traditional approaches, one uses a so-called materialized access, which relies on extract, transform, load operations, which extract the data from the sources and load it in an integrated data store, which could be a materialized knowledge graph, it could be a data warehouse. Instead, in the virtual approach, we don't do this, as I already mentioned before. We keep the data in the sources, and this data is only accessed at query time. So when a query is formulated, this query is transformed into a query to the data source. And this allows to avoid the costly materializations that then also would need to be kept up to date. And somehow in this way, one always has essentially fresh data that is accessed directly at the sources. And also, if one has a complex data management infrastructure that is already available in many organizations, one can just rely on this infrastructure to keep the data as it is and where it is. So this was motivating this approach to managing access and the integration of data sources. So let me now go a bit more in detail and discuss the components of the virtual knowledge graph architecture, and then how query answering works. And then I will say also a few words about the system that we have been building in Bolzano, which is the on-top system. And then I will spend some time on the design of a virtual knowledge graph system, on some considerations regarding the design. So we already saw this architecture. Let's now look at a bit more in detail at these various components of this VKG architecture. Specifically, we need to make some choices on the various languages that are used to define the ontology, to define the mappings, and also which is the query language that we want to use in this context. And one important consideration that one has to do in this setting is that we have to consider the usual trade-off that one has in situations where complex information needs to be managed, which is the trade-off between the expressive power of the formalisms that we are using to represent information, to query information, and the efficiency of processing the requests. There's always a trade-off between these two. And when making our choices, we have to consider this trade-off in light of some assumptions, which is, and the basic assumption is that we have large data sources that we want to access. And this needs to be considered. And several languages have been proposed for this setting, and these languages have been proposed in the context of semantic technology and of the standards for semantic technology and the semantic web. And here you see listed some of these languages, and also the years in which they were essentially defined as standards. So these are all recommendations of the W3C, the World Wide Web Consortium, and the recommendation of the W3C is a standard as defined by the W3C. And as you can see, the standards date back quite some years now. Specifically, the standard for the actual knowledge graph is RDF, so the data in which knowledge graphs are represented. The standard language for expressing the ontologies is the OWL2QL profile of the OWL2 language. which is a sub-language of a quite expressive language, which is OWL2. OWL2QL is a restricted language that is optimized for this problem of data access. Then there is a standard language for expressing mappings, which is the R2RML language, and the standard language for querying RDF graphs, and hence also virtual knowledge graphs, which is SparkQL. I will say a few words about this. Given the time that we have, we cannot go too much into detail, but I will just outline the main elements of each of these formalisms. So first of all, RDF. RDF is a formalism to represent data as a graph, and these graphs are represented as triples, so-called subject, predicate, object triples. And these triples are used, so each triple either relates two objects to each other by means of a so-called object property, or it relates an object to a data value. For example, an object is a person to a value which is the date of birth of the person, which is a value of type date, for example. Or such triples are also used to represent that certain objects belong to classes. For example, if I have the class of resources, then I could state that a certain web page is a resource. Or if I have the class of oil wells, I can state that oil well number 225 is an instance of the class of oil wells. So these are examples of statements that I can do with triples. Or I can state that in the context of university, I could state that an object student is related via the attends object property to an object of type course. So a student attends a course, for example. Now, I will not say much more about RDF. So it's essentially a way to represent graphs. It has also a way to linearize these graphs. It has its own formats to represent them, but this is all managed by our technology and by the tools that are being developed. The standard language for querying RDF is the SparkQL query language, which is has been defined in its latest edition in 2013. It's a language that is essentially based on graph pattern matching. So you can represent a SparkQL query, for example, the one here that is asking for the pairs ni, where n is of type node. This node should be connected to a router. Here I'm in the domain of systems, of web systems and networking. So this is another example where we're having a project. So in this case, I'm asking for nodes that are connected to objects that are routers, and I want to return the node and the ID of the router. And I can represent such a very simple SparkQL query, which this is just a basic graph pattern, by means of a graph, and essentially answering such a query amounts to finding a way to match this graph that represents the query structure, where I have nodes that stand for the verbs in the SparkQL query, and edges that stand either for connections, so properties that connect to nodes, or for the fact that a certain node should belong to a certain class. For example, N should be of type node, R should be of type router. So such a graph, I want to find a match of this graph in the graph that is my data, and answering a SparkQL query of this basic form amounts to finding such a match. And if I have more complex queries, I could have several such patterns, and they all need to match in a coherent way. Or in SparkQL, then one can combine these basic graph patterns via various operators. For example, union, there's an optional operator that allows to return an answer even if some part of the query doesn't match. There are complex filter conditions that I can impose on the objects and the values that I'm returning. There are also operations for aggregation, similar to what we have in SQL. And there is also additional possibilities, also forms of negative information. So SparkQL is a quite complex language that is managed, is the one used, a standard one in this setting. I don't have really time to go much into detail, but think of it as a way to match graphs into the data that is itself a graph, and then using more complex operators on top of that. Now, a few words about the ontology language on which we rely, which is the OWL2QL ontology language. Al2QL is one of the 3 standard sub-languages of this very expressive ontology language Al2 that has also been defined in the same standard as Al2QL. Al2QL itself is considered a lightweight ontology language. Why? Because it has a limited, I prefer to say controlled expressive power, where you are restricted in what you can express, but the advantage is that one has efficient inference. And specifically, this Al2QL language is optimized for accessing large amounts of data. And specifically, it allows for this rewriting-based approach, as we'll see in a second, where queries over the ontology can be reformulated or rewritten into queries expressed in the end over the underlying data sources. And this rewriting can be done while ensuring semantic and computational properties. So, and the fact that one can rewrite queries is tightly related to expressive power of the ontology language. If the ontology language is too powerful, this approach is not possible anymore. And one cannot reformulate SparkQL queries into SQL queries over the underlying data sources. And so also interesting to see that not only the query answering can be done by reformulating queries, but also checking the logical consistency of the ontology and the data can also be done by means of query evaluation. And the same techniques can be adopted also to check consistency of data and ontology. Just to give an idea of what we can express in this Al2QL language allows to express typical properties that one has in conceptual models. For example, subclass relationships, disjointness between classes, domain and ranges of properties, sub-properties. Also, properties can be navigated back and forth, so one has an inverse operator, so one can talk about the inverse of a property, and so there's no difference. One does not need to commit to one direction in which properties are considered. One can consider them in both directions. And in this sense, they are quite, this Al2QL ontology language is quite connected to conceptual data models. For those who are familiar with UML class diagrams, one can represent the basic elements of such UML class diagrams in terms of Al2QL assertions. And in fact, we also use UML class diagrams as a way to visualize and to interact with Al2QL ontology. It's a quite convenient representation for Al2QL ontologies. This has also been explored in a formal way quite extensively, this connection between conceptual modeling formalisms and ontology languages like Al2QL. So let me just now spend a few words on mappings, because the mappings are an important component in this virtual knowledge graph architecture and setting, because they encode how the data sources are used to create, how the data in data sources is used to create the virtual knowledge graphs, which is formulated in the vocabulary of the ontology. And the idea is that when we are in such a setting, as I was mentioning before, the queries are answered with respect to the ontology and the data in the virtual knowledge graph, which means that the mappings are then used to translate the queries of the ontology into queries down to the data sources. That's the idea of the use of mappings, and that's why we rely on declarative mappings. Essentially, a mapping consists of a set of assertions which map SQL queries over the data sources to class and property membership assertions. And the idea is that the answers returned by the SQL query in the left-hand side of the mapping are used to create the objects that populate the classes and properties in the right-hand side of the assertion. Notice that the mapping contains also a mechanism to transform the values that are retrieved from the database, such as numbers, strings, dates, and so on, into objects of the virtual knowledge graph. And in this way, one also solves the so-called impedance mismatch problem. Now, how does query answering in such a setting work? So the idea is that the ontology contains domain knowledge, and this domain knowledge, as was mentioned before, is used to enrich answers. So suppose that we are in this network setting, and suppose that we have data about printers. We know that LJ 2025 is a printer, and if the ontology states that every printer is a network device, if I pose a query that asks for all network devices, then I would expect to obtain also LJ 2025 as an answer, if I consider the knowledge in the ontology, because the ontology is telling me that every printer is a network device. And that's intuitively the way in which such ontologies are used. A very simple case in which we have a hierarchy, but there are more complicated cases in which one uses domain and range about properties, in which one uses information about mandatory participation to properties, also to enrich answers in this way. And this is how we use the domain knowledge. And in addition, the mapping encodes the information of how then to translate a query over the ontology, in which we have also then embedded the knowledge of the ontology into a query over the database. And a VKG query answering engine takes into account all these types of information. And this approach is called query answering by query rewriting. Let me just illustrate briefly the idea of what we mean by this. So we have a query over the ontology that you see there. The ontology is mapped to the data sources. Now, what we do is this query is considered an ontological query. There's a first step in which this query is rewritten with respect to the knowledge in the ontology, obtaining a new query, the so-called rewritten query, which is still formulated over the ontology. Then there's a second step, which is the so-called unfolding, although it's more complicated than view unfolding in databases. And this unfolding, but in the end, it produces a SQL query over the relational data sources that we assume to have available. And this takes into account the mapping information. This query can then just be evaluated over the data sources to produce a relational answer as the one produced by a SQL query. And then there's a further step in which the mappings are used to transform this relational answer into an ontological answer. For example, creating suitable objects corresponding to the classes in the ontology. And this is the answer that is returned to the user. So that's the general conceptual way, the conceptual architecture, conceptual processing of a query in such a virtual knowledge graph setting. Now, in practice, this is a bit more complicated. And we have built over the last 10 years a system in our research group, the OnTop system, that is a state-of-the-art virtual knowledge graph system that addresses several challenges that come up in this setting. It's compliant with all the relevant standards, the one that I mentioned, but also additional ones, for example, take into account geospatial information. It supports all major relational data sources, both commercial and freely available ones, like Oracle, DB2, but also Postgres, MySQL. And it also supports federation tools that allow to wrap sources and give them a relational view, like TAID, Dremio, and Denodo. These are quite popular data federation systems. The system that we are building is open source, and it's released under the Apache 2 license, which is a quite liberal license. So essentially, you can take the system and do whatever you want with it. Also build commercial applications. I don't want to go into detail. This is just the architecture of how actual queries are processed. So this should be contrasted to the conceptual architecture that we saw a few slides ago, this one, which is a conceptual framework in which queries are processed. Practically, the situation is a bit more complicated, and we distinguish between online and offline phases of query processing and various optimization steps which need to be carried out to make the system actually work in real-world scenarios. Yeah, so as I was saying, this is an open source effort, so there's a quite extensive developer community, not only in Bolzano and not only with our own spin-off, but various other partners that are involved in the development of this system, of the OnTop system. Let me now spend a few words, I would say the next 10 minutes, and then I would say we can then stop and have some time for questions on the design aspect of a virtual knowledge graph system. Because so far, essentially, I was telling you what is such a virtual knowledge graph system. But as I was mentioning at the beginning, in complex scenarios, these mappings and also the ontology can become quite complex. And so we need to understand and provide also support for setting up such systems if you want to use them in real-world situations. Now, first of all, let me say a few words about the ontology. So ontologies themselves might become quite large and complex, and designing ontology is a challenging task. Also, however, ontologies in many domains are already available. So ontology are widely used in the biological domain, for example, as we mentioned, the medical domain. They have been developed by experts about the domain in combination with ontology experts, and they are actually available to be used also in such virtual knowledge graph setting. And this ontology can be considered as standardized ontologies, and this also allows to interoperate between different domains and different systems. And as was mentioning, since ontologies are available since many years, also quite some advanced methodologies and supporting tools for ontology design have been provided and are available. Okay, for example, ontology design patterns, or the OntoClean methodology we just mentioned, developed by Guarino and Velti several years ago and refined over the years, allows to use sophisticated approaches and also tool support to develop ontologies. And one can also exploit, in fact, this correspondence between ontologies and conceptual modeling formalisms such as UML diagrams and ER schemas to also use frameworks and tools that have been proposed to design such UML class diagrams and ER schemas in various approaches, for example, in database design or in software engineering. Okay, so one can rely on all this technology to develop ontologies. The situation is a bit more complicated regarding the knowledge graph, virtual knowledge graph mappings. Why? Because these mappings, they map complex queries. We saw a mapping maps a SQL query over the sources to the ontology, to class and property assertions over the ontology. And in this way, they overcome the abstraction mismatch between the relational data and the knowledge graph. Now, these mappings are quite complex in the sense, and they are also more complex than other mapping approaches that have been proposed in related settings, but different settings. For example, in schema matching, where one wants to match relational schemas, or in ontology mappings. So these are disciplines in which mappings have been proposed. But the mappings used there are simpler than the ones in the virtual knowledge graph setting, which have, in addition to overcome this impedance mismatch between the data layer and the ontology layer. And in that sense, they are complicated. So this knowledge graph, virtual knowledge graph mapping design process so far is quite labor intensive, and it's a manual effort that is also subject to a lot of errors because people are not really familiar with how such mappings should be designed. And an important aspect to note is that the form of the mappings and the quality of the mappings hugely affect the performance of such systems. If the mappings are not designed in the proper way, such a virtual knowledge graph system will not be able to answer queries efficiently. So this poses quite some challenge on people who have to build, to set up such virtual knowledge graph systems. So I would say that managing the mappings and designing these mappings can be considered as the most critical bottleneck in the adoption of this virtual knowledge graph approach. Okay, I don't really have time to go into the details of real-world mappings, but this is just one example of a possible mapping that has been proposed in a context of the biomedical domain, where this is part of a running project in which we are involved, in which we are adopting this virtual knowledge graph approach in the context of biomedical ontologies. And you see that the queries that are used to extract the data from the actual data sources, which are quite complicated, can be quite complicated, and the way they are mapped to the ontology is also quite involved. So you can imagine that writing such specifications by hand is a quite challenging task in real-world scenarios. Now, several proposals have been made, and also tools that allow to design mappings have been proposed in various settings, and also in the simpler settings that I mentioned before. And many of these approaches are based on so-called mapping patterns. What is the idea of these mapping patterns? They are used in different methodologies for data management, for data analysis, and also in conceptual modeling. And the idea is that you define certain typical structures that occur in your data or in the schemas that underlie the sources that you have in your virtual knowledge graph setting, and also the structure that you have in your ontology. And essentially, you want to take into account the different kinds of information, which means information that is available at the level of the ontology, domain knowledge that is encoded in terms of the ontology axioms. But also, what is quite important in such a setting are the constraints over the relational sources, the constraints in your database schema. Typically, these are keys and foreign keys, and they affect the performance. So they affect the semantics on one hand, but they also have an impact on the performance if they are properly taken into account. Also, one might exploit actual data that is stored in the databases when this data is available the moment one is setting up such a system. Okay, if one has available data sources and one can access them, there is also often information, valuable information encoded in the actual data. And also, sometimes the relational data sources, they have a history of design and development that is often relying on some conceptual analysis phase in which conceptual schemas have been designed to produce the actual data sources. And often this information is reflected in the structure of the data sources. Often, sometimes it's also available, and one would like to exploit this information. And what we have done is we have defined recently a catalog of mapping patterns where all this kind of information is taken into account. And broadly speaking, we distinguish between so-called schema-driven patterns, which are essentially shaped by the structure of the database schema and the explicitly stored and available constraints, and so-called data-driven patterns, where one also considers constraints that emerge from specific configuration of the data in the database. Also, we have, for the schema-driven patterns, we have also corresponding data-driven patterns, where essentially the constraints are not explicitly specified. For example, a key constraint, if this is explicitly specified over a source, it can be taken into account in a schema-driven pattern. In some cases, whoever manages the sources might have disabled the key constraints or the foreign keys for various reasons related to the management of the source. But still, this constraint is either available and enforced on the data, or possibly not enforced through the database engine, but enforced through the whole context in which the database is placed. Sometimes perfectly enforced, sometimes the constraint is essentially enforced over the vast majority of the data. And this information can also be taken into account. We call such patterns that are based on constraints that actually hold over the data, although they might not be explicitly specified at the specification level of the database. We call these data-driven patterns. Then there are also data-driven patterns that do not have a counterpart in a schema-driven patterns, and we are also working and considering those. Let me just give you an example of one schema-driven pattern, which is, I would say, a very simple one. Actually, let me show two of them. The first one is the schema entity pattern, which essentially is saying that if I have an entity in my domain that is identified, where the tuples, the elements of this entity, are identified by some key attributes. Here I use K to denote the so-called primary key or primary identifier of the entity. Then I can map such an entity to a class in my ontology. So I map the entity to a class. I have a way to extract the identifier, to construct the objects in this class from the key in the entity, so from these key attributes. And then I can have additional attributes, and also the key attributes represented at the level of the ontology via properties, via object properties. So DA denotes a data property, sorry, by a data property, not object property. DA denotes a data property associated to an attribute A. And in this way, I can map an entity to a class, essentially. And this is the simplest form of the pattern. Then a bit more complicated pattern is one in which I have essentially three tables, one for one entity, one for another entity, one for an entity, one for an entity F, and the third table that represents a relationship between the two. And this situation can be recognized in the database because I have a primary key for this table that represents the relationship that is made up of two parts, which are foreign keys to the primary keys of the two tables corresponding to the entities. So this is a typical structure that I might find in a database. I can use this structure to extract the two classes corresponding to the two schema entity patterns that correspond to T and TF. And in addition, I can extract an object property that corresponds to this binary relationship between the two classes. And this is reflected in a common situation. And then I can have data that matches this pattern. And I would extract from data that corresponds to the situation with two entities and the relationship, I would extract a knowledge graph out of this. So, and I can define a mapping that would construct from data in such a table that corresponds to this pattern, would match this data, would map this data into an RDF graph. Very briefly, 1 second about a further pattern that is a data-driven pattern, which is also a quite common one, in which I use information inside, for example, a relational table based on some clustering attribute. So I have some attribute, for example, the gender, that allows to cluster the instances of this table that correspond to objects in my ontology into different categories. For example, suppose I have a gender attribute that has values male and female and other, for example, I could extract from this a class for persons with subclasses for male, female, and other gender, for example. So this would be a way to exploit the information inside an attribute, the gender attribute, to structure the data in my ontology into a class with various subclasses. And this is a typical data-driven pattern because you will not find the information at the schema level that corresponds to the structure in the ontology in terms of class with subclasses, but this information must be extracted from the data, for example, by looking at an attribute that allows to establish certain categories. Yeah. So now these mapping patterns that we have can be used in different design scenarios for virtual knowledge graph systems. For example, one might debug a virtual knowledge graph specification that is already in place and see whether the various mappings correspond to certain patterns or whether they fall outside the common patterns. One might do a reverse engineering of conceptual schemas from a database. So in this way, we can extract the conceptual schema corresponding to a given database. One might want to bootstrap mappings for a given database and ontology, where we have the ontology that is already given, but we map the connection between the ontology and the data. One might also bootstrap the ontology together with the mappings from a given database with constraints, and possibly also some information about the conceptual schema underlying the database. So in this case, we extract both the ontology and the corresponding mappings. Or we might also set up a full virtual knowledge graph specification from a conceptual schema of the domain. So these are all scenarios in which the patterns, similar to the ones that we have seen, we have more patterns for different kinds of structures, can be exploited in a suitable way. Let me just mention the on-topic spin-off that we founded in 2019, a few years ago, and that specifically develops technologies for designing such virtual knowledge graph systems. And we develop tools that help in the setup of such a knowledge graph, virtual knowledge graph architecture, the ontology, and specifically the mappings, relying on various information that is extracted from the information from the underlying data sources. And we also provide solutions for data integration and technical services related to this setting. So just to conclude, the virtual knowledge graph approach is a paradigm that is innovative, still not widely adopted, but we believe has a strong potential in every context in which one has to manage complex assets of information and integrate data. The design of the mappings is, I would say, the most challenging task in this setting and the major bottleneck. mapping patterns, eye promising approach. They are not the only way to proceed. It's not the only thing that we need, but they provide an interesting approach to design such virtual knowledge graph systems. And we have provided some initial work on this in this direction. Also, we have defined algorithmic techniques to extract semantics from relational data sources by applying this mapping pattern approach. And we have also developed tools to do this. Thanks a lot. And I'm happy to answer questions about it.
Thank you, Diego, for introducing the very important topic and also for sharing the most recent advances. Does anyone in the audience have a question? So feel free to unmute yourself and speak. Or maybe while the audience is thinking, I can start with a question that I'm sure if I don't ask, others will. So, about ChatGPT, of course. Very, very hot topic. So in the knowledge graphs domain, right? Also yes. the virtual knowledge graphs that Diego, you introduced. Somehow we assume there is some sort of ontologies available, right? It might need to be processed, but we do assume that there is some vocabulary describing a specific domain that is there. On the other hand, the things like ChatGPT or language model or machine learning in general, right? It learns directly from data or unstructured data. Yes. So what's your view on this comparison?
So in fact, I mean, I was concentrating here mostly on structured data because that's the direction on which we have worked so far the most. But clearly, we are well aware that structured data is not the only data. And in fact, we are now moving into the direction of dealing also with unstructured data. So sources coming from textual data, which are very important. And I believe these are two complementary directions that need to be put together. So the aspect of extracting structured information from textual data is an important direction. I mean, there is quite some work. And I believe that also possibly large language models as ChatGPT could be used in this context because they are able to somehow analyze in one way or another. I mean, we have seen the power of ChatGPT, but also we have seen some limitations that these systems have, right? Still, there's a lot of structured information that is embedded into text, and that such large language model would be able to extract. So, in fact, we are now considering to extend essentially the part that would deal with unstructured data, so as to propose and extract ontologies from the textual information that is available, from textual information that is available about a certain domain. Now, I guess that as always in these settings, I don't think it's possible to fully automate such a process, in the sense that the ontology that one extracts from in an automatic way from let's say textual information that is available then needs to be refined and validated. So it's unlikely that these ontologies or fragments of ontology will already serve the purpose of being used for data access. So then it will be a task to understand how to relate these extracted ontologies to already available ontologies that might be already available about a certain domain. And I see different approaches there. One is, again, by means of suitable mapping. So you would like to establish a mapping between the ontologies that one has already available about a certain domain and possibly automatically extracted ontologies, so that certain concepts that are extracted can be put into proper relationship with concepts that are already part of standard ontologies, for example. So this is definitely an important task. But for that, one can also use already available tools, because as I was mentioning before, ontology matching is a discipline that is well investigated. There are quite some proposals for that. And they could be readily exploited in this setting, because one would map then elements of the same way, ontologies to ontologies. Whether one can then also try to automatically map directly the extracted ontologies to the data, this is something that we are interested in exploring, actually. And in fact, we are currently working on proposals to apply this and to extend the approach that we are looking at with ones that are based on these large language models for extracting information and structured information from unstructured data.
I see. Thank you, Diego, for the thoughtful answers. So it is actually very much related to my own research as well. So I a personal view that I have is that in order to really be able to use these large language models, right, in a reliable, trustworthy manner, we actually still needed to rely on some semantic descriptions of what those kind of models are are able or not able to do to perform specific tasks. And in that sense, I think what you present here is also quite relevant. I mean, from the perspective of maybe simply using those large language models, right? I think it's useful to have also some sort of human understandable descriptions of the abilities of such models. And yeah, and this is very much related to things that we do here, actually. I have another more technical question, but I will keep it to the end. I will maybe leave first the floor to the audience. Gala, you have a question?
Yeah. So hello. I'm the second year PhD candidate in the Web Information System group. I also used to work on the knowledge graph, especially the knowledge-based question answering. So I know a bit about the Sparkle and the query language. So one thing I want to ask is about the because the virtual knowledge base, I see like you store the data in the heterogeneous format. I guess maybe just in the original data formulation, different tables. So maybe like if we want to execute some very complex queries, like that's maybe 4 or 5 operations, I'm thinking whether it will be quite slow compared to directly query the structural knowledge base.
Yeah, that's a key point. I mean, the efficiency of query processing. And I can tell you, as I said, I mean, the theoretical foundations for this technology and for this query transformation, rewriting and then unfolding go back to 2005, where essentially we defined the framework. And we built the prototypes at that time. By just implementing the basic techniques, we got very large queries, because if you start from a SparkQL query that has several basic trap patterns or other operators like optional and so on, and you combine these queries and then you apply all these transformations that we saw, the query grows quite a lot if you don't pay attention to optimization. And we had literally, from not too complex queries and not too large ontologies, we got queries, SQL queries that contained 100,000s of unions, literally. And they were not really efficiently processable. So the database engine couldn't even parse such queries. And that's why we have been working quite a lot on optimizing these queries. And in fact, we have developed quite advanced optimization techniques to take into account the various kinds of database constraints. They are very important in simplifying these queries. And now, essentially, we are able, in an automatic way, to generate automatically from the SparkQL queries, in the end, SQL queries to data sources that are as efficient as the ones that an expert person would write by hand, by spending a lot of time on trying to optimize these queries. So essentially, these queries are as good as they can get, which often means that they are quite simple queries without any additional joins with respect to the ones that you had. And then they can be processed quite efficiently. But this is a key point. I mean, and there is a lot of technology in query optimization that is involved in this process. And we exploit various techniques for semantic query optimization, distinguishing between online and offline phases of query processing. We do a lot of pre-processing before even queries are issued in order to compile information into the system so that then the queries can be rewritten efficiently. But this is a crucial point, fully.
Okay. Yeah, thanks. So yeah, a further question about this is, say, is there anyone, say, who think about like we generate, like transform part of the heterogeneous data into the triplet format, maybe RDF, but kept other parts. So then maybe it's a trade-off, like we use this space just for fast query, and other parts keep them original.
That's also one aspect we are working on explicitly. It's connected to data federation, because well, I mean, when we have heterogeneous sources, what we have is we have a federation tool as the intermediate layer, and this federation tool, they allow also to materialize part of the data. So you can also tell this tool to keep certain data materialized and keep other data virtual. And in fact, that's part of the optimization process, to understand which data should be better materialized. As you say, we construct either materialized relational data, or we materialize part of the knowledge graph itself, and we keep it stored. For example, if data is very static and doesn't change very often, then this might be a good choice, okay? And whereas other parts that are more dynamic, you keep them virtual because they would change and would need to rematerialize very often. And then you want to try to find the optimal trade-off between what to materialize and what to keep virtual, and then process queries in such a setting. That's something we are currently actively working on. And we call this framework ontology-based data federation, where the decision on materialization is part of the optimization choices that you make. Yes, it's a very good point.
Thanks.
Ziyu, go ahead.
Hi, thanks for the presentation. I'm having a question regarding the application of virtual knowledge graph. So I'm wondering what would be the use case where you can apply these knowledge graph by extracting the semantics from the relation data sources.
So essentially, this is not really bound to any specific domain. So we have applied this in many different domains. I mentioned the oil and gas sector. We had European projects where the partner was Statoil. Now it's called Equinor, which is the Norwegian oil giant. And they wanted to use this technology in the context of their data exploration department, which is made up of geologists who dig for oil and gas, and they maintain a lot of different data bases that are then integrated. This is one domain, but we're also applying this in the biomedical domain. We have now a running project in which we are using this in connection with biontologies about genes and gene expressions in the cancer domain. This is one other domain. The other domain in which we have been using this is the banking sector. So we have there in the company running projects in the telecommunication sector. So we are working with large companies that want to apply this kind of technology in the telecommunication sector. So it's not restricted to any specific domain. Obviously, having domain expertise helps in this, because in the end, you have to rely on information encoded, for example, in suitable ontologies. But in principle, this technology is domain independent and can be applied across different domains. We have used it in several domains, the ones that I'm mentioning. I mean, in these European projects, we are also using it in the context of innovation data. So we are collaborating since several years with a company in Spain that is using this technology to provide strategic consulting to research organizations who have to manage research and innovation related data. And this company is doing strategic consulting based on data analysis, and they use virtual knowledge graphs to essentially provide access to the information sources that are needed for their strategic analysis. that's another domain where we have concrete experience.
Yep. Thank you for answering.
Do we have one last question? We are looking at the clock. We are a bit over time.
For me, it's not a problem. I mean, I have enough time. So if you have any question, just
Then
go ahead.
maybe I can be a bit selfish and ask one myself again. Diego, you worked a lot on description logic, right? That's also quite a theoretical field, and at least from my perspective. So from what I understand, it's a subset of first order logic, right?
Yes and no. Yes, mostly yes.
And why it's no?
So no, because you have also constructs in description logic that go beyond first order logic. For example, reflexive transitive closure. In those cases, if you allow those constructs, then you are not in first order logic, because reflexive transitive closure is not expressible in first order logic. But the standard ontology language OWL2QL, and which is part of OWL2 and OWL2 itself, they have a first order logic semantics, so they fall within first order logic. And those who define the standard, they on purpose did not include constructs that go beyond first order logic. Yes.
I see. And then in these applications that you have mentioned, right? So it's actually also a question related to scalability. Do you encounter any limitations or hitting the wall of how of the feasibility, let's say, the existing theories?
Yes, definitely. So in the end, our 2QL is nothing else than a description logic. So our first paper was not came out before our 2QL was defined. This paper was in 2005, and the logic that we introduced was DL-Lite, which is a description logic. And now, as always, when you develop this kind of formalisms, you have to do a trade. I mean, there's this trade-off between expressive power and efficiency. And in DL-Lite and in our 2QL, we made some choice about what we allow and what not. Obviously, when people design ontologies, they would like to be as expressive as they can, right? And there are many foundational ontologies which are expressed in second order logic, and they would require second order logic to be fully expressed. Obviously, this cannot be captured, so one has to do some one has to take a compromise. So one has to resolve this trade-off in favor of efficiency, for example, and then you do not allow to use certain constructs. Just to give you an example, when I was saying that this OWL2QL and DL-Lite is very tightly related to UML class diagrams, right? We have studied this quite in detail, the formal correspondence between the two. Actually, this was still part of my PhD thesis. Before we had our 2QL and DL-Lite, I was studying for description logics, the correspondence between description logics and conceptual modeling formalisms like ER and UML class diagrams. And DL-Lite captures UML class diagrams, but it does not allow to capture, for example, complete hierarchies. So you cannot say that, for example, if in ontology you want to say that all courses are either bachelor courses or master courses or PhD courses, that would be a complete hierarchy. This cannot be captured in DL-Lite, because to encode this, you require union in the ontology. And if you allow for union, then you lose the property of this first order rewritability. So the property that queries can be rewritten, being sound and complete with respect to the semantics. So you have to make a trade-off there. You do not allow to express this covering these complete hierarchies, right? So you lose expressive power, but this is in favor of being able to have efficient query processing. And clearly, there are also practical limitations, because in practice, people would like to express more, but then they have to just stay and live with the limitations. We have then also developed, and others have also developed, then techniques to partly overcome these limitations. So there are different ways related to the mappings, related to the query language, to go beyond these basic limitations and try to get more expressive power. For example, one can embed certain semantics inside the mappings, and in that way gain additional expressive power in a controlled way, still being careful about what you do, but there's a lot that can be done in that respect. But yes, clearly these are limitations that also affect practical encoding, practical formalization of practical problems.
I see.
But that's what we have to live with.
I see. Well, this is super interesting. I wish I can continue this conversation for longer, but I'll keep it for the future. Do we have maybe one last question from the audience? If not, then let's close it here. Thanks again, Diego. It's great pleasure to have you here.
Thanks a lot for inviting me. It was nice to have the chance to give this presentation.
Yeah. Thanks for the presentation.
Thank you.
Thank you so much.
Bye-bye.
Thanks everyone for joining the Academic Fringe Festival. See you next week.
Bye-bye.
Bye-bye.